Hi, thank you so much for joining me again, or for the first time maybe. In this segment, what I want to look at is our phase changes from a molecular and an atomic view. And this would be something I would cover in my AP/IB or when I teach general chemistry at college. And I like to really make a good comparison of what we are breaking. In this case, these are melting points. So, and it takes to break when melting, or the opposite, what is freed to form when things condense into a liquid or then go on further to form solids. Now, I went ahead and put some ranges of melting points so you can get an idea of what we're looking at. If we have network covalent, and I like to ask my kids to always classify, is it network covalent, metallic ionic, or molecular covalent? For example, this is a glass, and there are lots of glasses. They're doped have different properties. To melt this, we actually have to break a covalent bond. So you're breaking a bond. That's a very strong force of attraction. Those melting points are very, very high. This gives you kind of the range, on the order of 1400 to 3500 degrees. If you're looking at metallic, to melt it, you have to break a bond, that attraction between the sea of electrons and the valence. Freed valence electrons. There's a pretty broad range here of what it takes to break or what is freed when it forms. Okay, so I personally don't think you're ever going to see questions asking you to compare metallic, ionic, or covalent, because ionic are also strong. You're breaking that Coulombic attraction when melting, and they can be over 3,000. There's a lot of overlap when we are breaking bonds. And so I really think you are going to get data to help you make that determination, right? As you increase your force of attraction, you're going to increase the energy that it takes to break, and you're going to increase the melting point. And the boiling point. We're looking at melting points here. Now, contrast that to our molecular covalent. How much lower those tend to be. And that's because we're not breaking bonds. In this case, we're breaking intermolecular forces of attraction. If we're breaking it, we would free energy to form it. I hope I'm saying that enough times. So here we would be breaking a hydrogen bond, breaking dipole-dipole, breaking London dispersion. And we have quite the range, and it tends to be much smaller, much smaller than energy required to break than when we're breaking actual bonds between neighboring atoms. These are forces of attraction between neighboring molecules. Okay, so I wanted to make that point. Now, the other point that I like to make as we look at kind of the more atomic molecular view, where you'll often see particle diagrams, is I like to look at ionic compounds and the effect of lattice energy on melting points. And let's take a look at the definition of a lattice energy. Now, I don't at my level get into crystal structures, so we're very simply going to be looking at a potential energy Coulombic effect. The lattice energy is defined as the energy, and let's think about it, we have a cation and an anion forming an ionic compound. So it's defined as the energy freed to form, or the released energy when you form. So it would be negative. We can also look at the energy that it takes to break these, and If you have more energy released, it takes more energy to break, and you're going to have an increased melting point. Okay? So if we look at Coulombic attraction, remember if you increase your charges, we're looking at positive and negative, or decrease your distance, you're going to have a greater energy released. It will be, the lattice energy will be more negative or lower. Okay, so let's compare two of these. We have sodium oxide, and I want to compare it to aluminum oxide. So when you do that, I think it's really helpful. I almost put potassium, whoops. Let's take a look at sodium ion compared to the aluminum ion. Now the oxide is the same in each of these, so we really only have to compare the cations, and we want to look at charge and we want to look at distance. So let's see who wins. Well, I think it's pretty clear. Aluminum wins based on charge. And if you look at the periodic table, you will see aluminum also wins on distance. I tell my students if it's a tie, if one wins on charge and one wins on distance, that charge typically trumps distance. Charges are going up by multiples, and distance is not always changing or doubling and tripling. Okay, so if you have to make a choice, that's the choice I would make. So that tells me that the lattice energy for aluminum oxide is much greater. And notice that you see that as this huge difference in their melting points. These are their lattice energies. Now, if you look at their melting points, I made a little cartoon for my students, but I'll write them in here. The melting point for sodium oxide is 1132 degrees Celsius. I would say ish from the source I got that. And for aluminum, it is 2054 degrees Celsius. So when you see this very large increase in lattice energy, it's going to be reflected in a much greater melting point. And so I guess I was in a silly moment, so I made just a little cartoon for my students saying that there is a relationship between lattice energy and the melting points. And again, Coulomb's law is your very, very, very good friend, especially in AP chemistry. Thank you so much for joining me.